Hello everyone, welcome to the session of Design of Machine Elements 1. So I am Purushotham, working as Assistant Professor in the Department of Mechanical Engineering, Maharaj Institute of Technology, Mysore. So today's session is about stress concentration. Stress concentration. So stress concentration is defined as localization of maximum stress due to irregularities or abrupt changes of cross section. That means in a machine element or a component, when there is change in cross section, that may be walls or shoulders or fillets. So due to that, the stress will be localized at some point. So that will be the maximum one. So which is called as stress concentration. To understand this, I am going to refer these two figures, figure 1 and figure 2. So if you can see this, first I will consider a solid rectangular plate, that means which is having some width and length as well as the thickness. Which is subjected to the tensile load, so these will be the force lines, force flow lines, that is A, B, B, C, C and D, D. These are the force flow lines. Now I am going to take a section at 3 different places in the rectangular plate. So the section planes are X, 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 Y, Y and Z, Z. So when you are going to take a section, now I am going to calculate the stress induced in the rectangular plate due to the applied tensile load. So that is, when you are going to calculate, for example, if you are going to calculate at this point, then you will get some value. That is the stress, the tensile stress which is given by load by area. So this will be the force line, that is load line, the area, that is the width and the thickness, multiplication of width and the thickness, that will give you the cross sectional area. Then you will get some stress value, that is I am going to call this as sigma T, stress induced due to the tensile load. In the same way, if you are going to calculate the stress at this point on the same XX sectional plane, then you will get the same value. So the value may be, for example, I will take around 50 megapascal. So here also you will get the 50 megapascal. In the same way, if you are going to calculate the stress on the YY sectional plane, then also you will get the same value, that is 50 megapascal. So that means, so further if you are going to calculate at the sectional plane ZZ, then also you will get the 50 megapascal. That is the stress which is uniform throughout the plate. So from this, so we can calculate the stress at any point. That means the force lines are which is parallel to the load axis. Due to that, the stress at each and every point, so which is same. So which is homogeneous material. Now coming to this one, so this is also a rectangular plate, but which is having a circular wall at the center. So which is subjected to a tensile load of F. Now you can see this, the force lines, the force flow lines near the circle, near the wall, so which is clustered. That means which is not parallel to the loading axis. That means the stress lines or force flow lines which is accumulated around the hole. You can see this. Now, if you are going to take a section at 3 different places, for example, I will take this as X sectional plane, this will be Y, this will be Z. Now, if you are going to calculate the stress at X sectional plane, somewhere you will get the value as 50 megapascal, but when you are going to calculate the stress at Y sectional plane at this point, then you will get the value which may be around 80 megapascal. That means the stress which is not uniform throughout the material, but whatever the stress, so which is increased around the discontinuity of the material. Here discontinuity is wall. So around the wall, the force flow lines or stress flow lines which is clustered, accumulated. So where we can see the maximum stress. So that is accumulation of the stress around the discontinuity or clustering of stress lines near the wall, which is called as stress concentration. That means around when there is a discontinuity in the material, So around the discontinuity, you can see the clustering of stress lines where the stresses which are localized, that means at some localized point the stresses will be maximum, which is called as stress concentration. Now coming to this, the cause of this stress concentration, the things which is going to cause this stress concentration, which is called as stress risers, which is called as stress risers. So the principal cause of stress concentration, that is due to some geometrical discontinuities like holes, notches, fillets, shoulders, threads, or internal defects like some voids or cracks. So then the load discontinuities. So maybe at some point there will be static load, suddenly there will be impact load or fatigue load. So that is also cause the stress concentration. So these things, the geometrical discontinuities, holes, notches, fillets, these are the essential stress risers. Just because as we know that, so the machine which is not a single component, the machine which is assembly of many components or many machine elements, when you are going to assemble one component with another, then we are going for some threaded fasteners or some we go for keyways, all those things, or internal threads like this. So for this, we can't eliminate the stress concentration, but we can reduce the stress concentration. So we can see this. So there will be a shaft. The shaft. So if you want to transmit the power from one shaft to another shaft, then we have to transmit by using machine elements like gears or pulleys. Then we need to mount the gears or pulleys on the shaft. So for that, we are going to make a slot, that is keyway slot on the shaft, as well as we are going to use the keys to lock or to mount the gears or pulleys. So then only we can transmit the power from one shaft to another shaft. That means these are essential where there is a keyway slot, that is discontinuity in the material, where we can see the maximum localization of stress. But we can't avoid this, but we can reduce the stress concentration effect. So by using some methods, for example, you can see here, so a plate with a hole at the center. So that will shows the clustering of stress flow lines around here. So if you want to reduce this, so this will be the bad design. We can call this as bad design, or we can use the better one or preferred design is this figure. That means by making multiple holes in a plate, then you can observe this, the clustering which is reducing, the clustering around the holes which is reducing. Now you can see at the ends the force flow lines which is almost become parallel to the load axis. So that means we can reduce the stress concentration by making multiple holes in a plate. Then here also you can see this, there will be a sharp corners. So here the diameter which is going to this will be the plate. So here the width which is going to reduce, here they are using the sharp corners. Around these sharp corners, so there will be a clustering of stresses. So this will be called as bad design. So instead of this, so if you are using, instead of sharp corners, when you are going for the fillets, so then the force lines, clustering of the force line which is reducing. So this will be called as preferred design. So like this way, so we can use, so instead of making single notch in a component, we can use the multiple notch, then we can avoid the clustering of the force lines. Then instead of using small diameter length of the threaded one, we can use the larger diameter threaded length, then we can reduce the stress concentration. Now to calculate the stress concentration or to take the effect of stress concentration, so then we go for the stress concentration factor. That means to take, when you are going to design any machine component, so these are the things in which is common in the machine elements. So somewhere there will be a hole or the fillets, shoulders or the grooves, all those things are present. To accommodate this effect, stress concentration effect, we are going to take the stress concentration factor. We are going to calculate the stress concentration factor. The stress concentration factor that can be calculated by using two methods. The first one is mathematical analysis by using theory of elasticity concept. So that means by using theory of elasticity concept, we are going to calculate the stress concentration factor, that is preferably theoretical stress concentration factor. Then another method is experimental one. So by using finite element methods, brittle coating method, photoelasticity method, as well as electrical strain gauge method, we can calculate the stress concentration factor. So in design of machine elements 1, so we are going to calculate the theoretical stress concentration factor by using theory of elasticity concept, that is mathematical analysis of theory of elasticity concept. So for this stress concentration factor is given by, so the general expression for stress concentration factor is maximum stress by nominal stress. So this will be the generalized expression, that is maximum stress by nominal stress. If the material which is subjected to the direct stresses, or we can see this, so what we need to calculate, the maximum stress induced in the material, that is sigma max is given by what? Sigma nominal into stress concentration factor. So I will use KT here, KT. So KT will be the notation which is used for the stress concentration factor when the member which is subjected to direct stress and bending stress. Now when the member which is subjected to the direct stress, then the maximum stress induced in the material, which is given by sigma max, which is equal to sigma into KT, where sigma which is given by force by area into KT. So this will be in the data handbook. Equation number is 2.1a, then page number 20. So KT, which is the symbol notation used for the stress concentration factor for the direct stress and the bending stress. When the material which is subjected to bending stress, then the maximum stress induced in the material which is given by sigma b into KT, as we know that sigma b bending stress which is given by m into c by I into KT, or we can say m by z, that is sectional modulus into KT. So this will be also available in the data handbook, equation number 2.1b, page number 20. Then for the shear stress, that is when the member which is subjected to the torsional load, then the maximum stress, that is tau max, which is given by tau into Ks. Here the Ks will be the notation which is used for the stress concentration factor when the member which is subjected to the shear stress or torsional load. Now as we know that the tau, the shear stress which is given by T into R divided by J, or we can say T by Zp, that is polar sectional modulus into Ks. So this will be the expression, so which is also available in the data handbook 2.1c, page number 20. So these things where KT and Ks, these are the theoretical stress concentration factors which depends on type and size of discontinuity. For example, the discontinuity is hole. So the size will be around 15 diameter or 15 mm or 20 mm. That is the type of discontinuity is hole and size is 20 mm or 25 mm. So these KT and Ks values which is depends on size and type of discontinuity. Then the estimated stress concentration factor, or we can call it as actual stress concentration factor, so which is given by KTF, so which is equal to 1 plus Q times of KT minus 1, so which is available in the data handbook, equation number 2.5, page number 21. So we can't only consider the type and size of discontinuity, that is the type of the material as well as type of loading. So on that material or component which is going to subject it to, which is also matter, to accommodate these things we are going to take estimated stress concentration factor, or which is also called as actual stress concentration factor. So that is KTF, which is equal to 1 plus Q times of KT minus 1. So here the Q, which is called as notch sensitivity index, notch sensitivity index, the magnitude of this Q value, notch sensitivity index, which depends on type of material as well as type of loading, then this one, the magnitude of these Q values, which is less for ductile material and more for brittle material. Now based on these equations for several type of discontinuities, we are going to calculate some stress concentration factor. Now, so let us see some cases in the stress concentration, that means based on some type of discontinuities. So we are going to calculate the stress concentration factor. So for this, first I will read out the problem. A rectangular plate of 60 cross 80 millimeter with a hole is 15 millimeter diameter in the center is loaded axial tension of 25 kilonewton. Thickness of the plate is 10 millimeter. Find the maximum stress. That means they are given a rectangular plate. So first I will draw out a rectangular plate, so which is having 60 cross 80 millimeter. That means they are given the width of the plate, which is 60 millimeter, and length of the plate, that is 80 millimeter, and with a hole of 15 mm diameter in the center. That means there will be a circular hole which is present at the center of the plate. The diameter of it is 15 mm. So at the center I am going to draw one circle, that is hole, which is having a diameter of 15 mm and which is loaded axial tension. That means the material which is subjected to loading of tension, so the value is also given 25 kilonewton. Then thickness of the plate is 10 millimeter. So they are given the thickness of the plate. For this I will just draw one side view. So from this we can visualize this will be the width of the plate, that is 60 millimeter, and this will be the thickness, that is 10 millimeter. Thickness is 10 millimeter. This will be 60 cross 80, and this will be the diameter of the circle, and this will be the load, tensile load. Now, so we drawn out the extract the figure based on the statement. So to calculate the stress concentration factors in the data handbook having several figures, so we need to identify the figures, so which is having similar case, exact case. So by doing this we can calculate the stress concentration factor, as well as in terms of that we can calculate the maximum stress induced in the material. So for this, if you are seen in the data handbook, then from figure 2.12, that is stress concentration factor for plate with a hole in tension, which is present at page number 36. If you observe this figure, you can see this. So this will be the figure in the data handbook, which is exactly same case as that of the given problem. That is, there will be a rectangular plate which is having a hole at the center, so which is having some breadth, as well as which is subjected to tensile load, as well as which is having some thickness. So I am going to refer this figure to calculate the stress concentration factor. Now which is subjected to tensile load, that means direct stresses. For this, the maximum stress induced, which is given by sigma into KT, So sigma, which is given by force by area into KT. So first I will calculate the nominal stress, that is force by area. Force is given 25 kilonewton. I am going to convert it into Newton. 25 into 10 power 3. Then area, to calculate the area, in the figure itself they are mentioned how to calculate the area. So the rectangular plate with a hole, for that they are mentioned the equation to calculate the area, that is B minus A times of T. So here first I will identify, so the B value, which is nothing but the width of the plate. So for width of the plate I am going to write here, B value is width of the plate, that is 60 millimeter, and A value, which is diameter of the hole, that is small a, which is 15 millimeter, and then thickness value, which is given by notation T, which is also given 10 mm, and the force, so they are using notation F, which is 25 into 10 power 3 Newton. Now I will calculate the area, which is given by B minus A times of T, so which is given by 25 into 10 power 3, B is 60 mm, A value is 15 mm, and thickness is 10 mm. If you are simplify this, then you will get sigma value, that is nominal stress, which is 55.55 Newton per millimeter square. Now in this equation we found out the value of sigma. If you are able to calculate the value of this stress concentration factor Kt, then we can find out the maximum stress induced in the element. So for this I am going to consider this figure. Here in the x-axis you can see A by B, the ratio of A by B is given, so which is notated, that is 0, 0.1, 0.2, 0.3, 0.4, like this. In the y-axis you can see the stress concentration factor, so from 2.1 to 3, they are given from 2.1 to 3. So to accommodate this, so first I will calculate this ratio, that is A by B. So we know that A value is 15, B value is 60. So if you calculate this, then you will get 0.25. Now I am going to mark the 0.25 on the x-axis, A by B ratio, that is this will be 0.2, 0.3, so somewhere here, so this will be 0.25. Then from here, from this point I am going to draw a vertical line, so which is going to intersect the curve, the figure which is having curve, which is going to intersect at somewhere at this point. So from here I am going to draw horizontal line towards y-axis, so that is going to intersect here, that is the y-axis which contains value of stress concentration factor. Now if you are able to understand this, this will be the 0.25. From here I am going to draw the vertical line which intersects the curve. Then from here I am going to draw the horizontal line which intersects the y-axis, which contains the values of stress concentration factor, that is, so which is around, so from the calculation we will get Kt value, which is equal to 2.46. So if you are calculate by using scale, and so that will be get at 2.46 Kt, which is equal to 2.46. Now in this equation we got to know the sigma value as well as the Kt value. Now I am going to calculate the maximum stress induced, that is sigma max, which is equal to sigma into Kt. So I know the value of sigma, that is 55.55, and Kt, so which is 2.46. So if you solve this, then you will get 136.66 Newton per millimeter square. Sigma max, which is equal to 136.66 Newton per millimeter square. So conventionally if you are calculating the normal stress, then you will get 50.55, but due to the presence of discontinuity, a circular hole, so the maximum stress induced in the material, that will be rise to 136.66 Newton per millimeter square. So next we move on to the problem. So here the discontinuity which is in the type of step shaft as well as the fillet. So for this, if you have to observe this symbol, the shaft, this symbol which represents the shaft. So for this case, that means this will be the 75 mm diameter which is stepped down into 50 mm diameter, then the fillet radius is 10 mm, then which is subjected to bending moment. That means in this machine element which is bending stress will be induced. So for this machine member, we need to find the maximum stress. So then we have to take the accountability of stress concentration, just because of this will be the discontinuity in the cross section, like step shaft as well as the fillet radius is present. So before that, we need to figure out the same exact case in our data handbook. So that means the step shaft which is subjected to bending moment which is having some fillet radius. So then only we can correlate with this problem to find out the stress concentration factor KT. So if you are looking to the data handbook, the figure number 2.25. So that will represent KT for a step shaft which is subjected to bending load. So this figure will be present at page number 43. So if you look into the figure, so the step shaft which is subjected to bending load, the same exact case. Now I can relate this figure with the present problem to find out the KT value. So for this, so you can look into this. So here first I will figure out the dimensions. The capital D here, the main diameter, that is 75 mm. So first I will extract the data, that is the capital D is 75 millimeter, which is stepped down into 50 mm, which is notated by, that is small d. So small d which is given by 50 millimeter. Then radius of fillet, that is represented by small r. So here also which is given by small r, that is 10 millimeter. Then which is subjected to bending moment m. So that is 70 Newton meter, but we are representing in Newton millimeter. So just because the m which become equal to 70 into 10 power 3 meter which is converted into millimeter. As we know that to find out the maximum stress, then the equation is given by sigma b into KT, that is stress induced due to bending load as well as the stress concentration factor. Now to find out the sigma b, we know that sigma b which is given by m into c by I, then here m is the bending moment. I am taking c in the numerator to the denominator of denominator, that is I by c. So if you look into the figure, the I by c value which is given as pi d cube by 32, here small d is used just because this will be the critical section. We can't take the 75 mm as the d value, we have to take the small d, critical section diameter 50 as the d cube value. So m by pi d cube by 32. So I am going to substitute this value, sigma b which is equal to m is 70 into 10 power 3, then pi small d value is 50 mm, that is 50 cube by 32. If you solve this, then you will get bending stress which is equal to 5.7012 Newton per millimeter square. So this will be the bending stress value. Now, so in this equation, we need to find out the sigma max. Now I know the value of sigma b. If you are able to calculate the stress concentration value, then we can easily find out the maximum stress induced. To find out the KT value, I am referring this figure. Here you can see in the x-axis, in the abscissa, we can see small r by d ratio. So first I am going to take this as small r by d ratio. So r by d ratio, here in this problem r is 10, small d is 50. If you solve this, then you will get 0.2. Then in the figure, there are many curves in that which is given by the ratio of capital D by small d. So here also I am going to take the ratio of capital D by small d, that is capital D is 75 mm, small d is 55 mm. If you are going to solve this, then you will get 1.5, which is the ratio of capital D by small d. Now, I am looking to the figure here in the x-axis R by D ratio, which is for the present problem is 0.2. I am going to take a 0.2 on the x-axis. Then from this I am going to draw one vertical line, so that will intersect a curve. Which is having a value of 1.5. We need to identify the curve which is having a D by D ratio of 1.5. That will intersect the curve which is having a D by D ratio of 1.5. Then from here I am going to draw horizontal line that is going to intersect the y-axis, so which represents the KT values, So if you are able to see this, then the KT value which is 1.42. So by using scale, if you do this problem, then you will get exactly 1.42. So this will be the KT value. So now KT value is known, sigma B value is known, but mainly one thing is they are given Q value which is equal to 0.95. That is the notch sensitivity index. That means the KT value, theoretical stress concentration factor, which is only taken account of type and size of the discontinuity. The Q value which is going to take account of type of loading as well as the material. Now, if you need to calculate the sigma max value, then the equation which becomes estimated stress concentration factor KTF into bending stress. But we found out the KT value, so we need to find out the KTF value. So KTF which is given by 1 plus Q times of KT minus 1. This will be available in the data handbook, 1 plus Q times of KT minus 1. So if you simplify this, 1 plus Q is 0.95. So KT value is found out, that is 1.42 minus 1. So if you simplify this, then you will get 1.399. Now we are going to find out the maximum stress induced, that is sigma max, which is equal to KTF into bending stress. Now KTF value is 1.399, bending stress is 5.704. So if you are simplified this, then you will get 7.98 Newton per millimeter square. So this will be the maximum stress induced in the machine member due to stress concentration or discontinuities. That means in the bending stress, if there is no discontinuity, the bending stress will be induced at 5.70 Newton per millimeter square. Due to the discontinuity in the machine member as well as the fillet radius, there will be a stress concentration that will increase the stress induced in the machine member, that is 7.98 Newton per millimeter square. So like this we are going to solve the discontinuities, maybe the grooves, notches or fillets. So for this type of problems also we need to refer the figures in the data handbook that will be matches exact case. Then from that we can find out the stress concentration factor as well as the maximum stress induced in the machine member.